All right, today we're diving into something really ambitious. We're talking about a blueprint for a next-gen antiviral, one that's designed to be, get this, escape-proof. So let's break this whole thing down, piece by piece, and see exactly how it plans to outsmart even the trickiest viruses.
I mean, that quote says it all, right? Ready to make some viruses wish they'd never evolved. That just captures the sheer audacity, the confidence behind this whole idea. We're not just talking about another treatment here. The goal is to build a system so tough that a virus evolving to beat it, well, it becomes basically impossible. So, how do they plan to pull that off?
Okay, so the core idea here is all about a multi-layered attack. See, if you just hit a virus with one thing, it's got a fighting chance to evolve and dodge it. But this blueprint, it goes for a simultaneous three-pronged attack. It's like a coordinated assault from three different directions at once. Let's dig into the engineering of each of these weapons.
First on the list, the entry shield. This is your frontline defense. Its job is to stop the virus dead in its tracks, out in the bloodstream, before it even gets a chance to knock on your cell's doors. It's not just a lock. Think of it more like an elite security team patrolling the perimeter, ready to intercept any threat.
So this is where it gets really clever. The problem with a simple decoy trap is that a virus will eventually, evolve its way around it. It's like having a single lock on a door. Sooner or later, someone's going to pick it. The fix? They made it bi-specific. It grabs the virus in two different spots at the same time. Think of it like adding a deadbolt and a chain lock. For the virus to escape, it would need to mutate in two specific ways at the exact same time, which is just incredibly unlikely. And then there's the dosage issue. To solve that, they use self-amplifying RNA, or saRNA. This basically turns our own cells into little decoy factories, pumping out 100 to 1,000 times more of these molecules. Just brilliant.
Okay, but what if a couple of viruses are sneaky enough to get past that entry shield? Well, that brings us to the second line of defense, the genome shredder. And yeah, it's exactly what it sounds like. If a virus makes it inside one of our cells, this system is designed to find its genetic blueprint, its instruction manual, and just tear it to shreds.
Now, the first draft of this shredder was powerful, for sure, but totally impractical. It needed a huge amount of RNA to work, which would have been way too expensive to make at pandemic scale. So, the fix was to get smarter, not bigger. They used some heavy-duty analysis to pinpoint the parts of the virus's genes that never change, these hyperconserved spots. By targeting those, they needed way less RNA. And the safety switch? The original idea needed you to take another drug to turn it off. The new design has an automatic self-destruct switch that just shuts down the shredder when the infection is gone. It cleans up after itself. How cool is that?
And that 10x number? I mean, that's not just a small improvement. A tenfold reduction in how much RNA you need is an absolute game changer. It's the difference between a cool idea on a whiteboard and something you could actually mass produce for the entire world in a crisis. It makes it viable.
All right, we're on to the third and final prong of the direct attack, the pan-enzyme inhibitor. So, let's say, against all odds, a piece of the virus's genetic code survives the shredder. This thing is designed to be the ultimate wrench in the works. It basically jams up the virus's internal factory, stopping it from making copies of itself. And here again, we see this pattern of smart upgrades. The original inhibitor had two big problems. You needed a really high dose, and it was coated in a material called PEG, which can cause allergic reactions. So what do? First, they redesigned the inhibitor to be 100 times more potent, so you only need a tiny amount. Then, they swapped that PEG coating for something called polysarcosine, which is basically a stealth material. It's totally invisible to your immune system. More power, less risk. Win-win.
Okay, so that's the three-pronged attack to stop an infection in its tracks. But this thing is designed to do more than just fight the current battle. It's also about winning the war. It has a whole other component designed to train your immune system, creating long-lasting immunity, so your body knows how to defeat the virus all on its own next time.
And once again, it's all about making the design practical. I mean, the first version of the vaccine hydrogel was so big you literally couldn't inject it. Not very helpful, right? The fix was to use a smart algorithm to pick out only the most effective little pieces of the virus, shrinking the whole thing down to a standard injection size. And they did the same thing with the immune booster it used. They swapped out a drug that caused nasty side effects for a much safer, targeted one that only works right where you inject it. No more systemic issues.
So, we've got all this incredibly powerful biotech working inside the body. The big question is, how do you make sure it's all safe? Well, that's where the fail-safes come in. The blueprint is packed with clever safety switches to make sure the whole system can be watched and, if anything goes wrong, shut down in an instant.
To know if it's working, you need a sensor, right? But the original sensor design was, well, kind of flawed. It was too fragile to survive in the bloodstream, and it needed a surgically implanted pump, which means years and years of regulatory hurdles. The fix is just genius. First, they beefed up the sensor itself to make it more durable. And second, they ditched the complicated implant for a simple microneedle patch, just like the ones used for insulin. That's a technology that's already approved. It completely short-circuits the regulatory nightmare and makes this so much closer to reality. And then you have the ultimate safety net, the big red button, the universal kill switch. If there's a serious problem, a single shot administers a special molecule. This molecule finds and disables a key protein that the whole therapeutic relies on to function, and within 30 minutes, everything shuts down. It's a fast, total, system-wide emergency brake.
Okay, so the science is elegant, the safety features are incredibly well thought out. But that brings us to the bottom line, right? Two huge questions. What would this actually cost to produce? And how do we even know if it really works?
All right, let's look at the costs. We'll start with the most complex piece, the self-amplifying RNA decoy. That's estimated to come in at around $8 a dose.
Next up, you add the genome shredder and the pan enzyme inhibitor. Those two together would add about another $10 to the total. And finally, you've got the vaccine part and the sensor patch for monitoring and safety. That's another $7 combined.
So you add it all up, and the grand total for this entire, super sophisticated course of treatment is about $25. $25. Just to put that into perspective, that's way cheaper than something like Paxlovid, and it's just a tiny fraction of what monoclonal antibody treatments cost. It's astonishingly affordable. And finally, let's talk about success. The designers set an unbelievably high bar here. They call them non-negotiable gates, basically pass-fail tests. It has to slash the virus by 99% in just 24 hours. It has to get to zero detectable virus in 48 hours. And to prove it's truly escape-proof, it can't produce any resistant viruses after a month of being put to the test. Oh, and it has to completely clear out of your system within 10 days. No compromises.
So when you step back and look at the whole picture, this multi-layered attack, the long-term immunity, the built-in kill switches, the crazy low cost, and these incredibly strict rules for success, it really leaves you with a massive question. Is this kind of thoughtful, powerful, and practical blueprint the future pandemic preparedness? It's a pretty compelling vision, that's for sure.